is not going to be able to join.
Yes,
good to see you as well, Karen.
I remind him through WeChat, but there is no response. But I think you can start on time.
Okay.
And there are two guys we cannot contact them. One is Lakshi from Mahindra University. And another guy is Suman Biswas from Korea. He told us he canceled the presentation. Maybe tonight we can complete the session a little bit early, because in the previous sessions we almost every time we spent 4 hours. It's too long.
No, I can't. Yeah,
we can't do that. David, I'm wondering, in settings, can you change your background audio? No, your background audio, because we are picking up stuff from
Am I picking up a lot of background?
Yeah, okay. And so there's like 4 settings, and I think if you set it to the higher one, it might work a bit better, especially since you are using a mic.
So I've got automatically adjust noise suppression, low, faint background noises. How about that? I've now changed it. Is it picking up the background noises?
Yeah, that's actually worse.
Yeah, yes.
How about this?
That's much better for me.
Better.
Okay. So
I mean, I can hear the guy pounding on the counter there with the espresso thing a minute ago.
Can you hear me now? Is it all fine? I can adjust the volume mic as well.
Yeah, no, you're fine. That cleared out the background pretty well.
Excellent.
I'm getting used to this. Right across the street from my office is a pile driver right now. I'm not in my office today, but for that reason. But we have pile drivers, so noise suppression is important.
Yeah, well, if you have a minute to understand my situation, so I've due to go down to London, and there's a train strike, so I've had to drive, and it snowed yesterday, so there was a crash on the road, so I didn't make it to where I intended to be, and just stopped here on where I could.
And we're all going to laugh because we know that it was probably less than a centimeter of snow, right? The Canadians in the room will laugh.
They will. But I didn't see the accident. It was just the aftermath. Okay. So, Kiwei, are you still there? Kiwei?
Yes, I mute myself. I think you can start on time.
Yeah. I was about to start. I just wanted a reminder who is not going to be delivering, so I'll just cross them out and I won't introduce them.
Durai will join us later, actually.
Okay.
I think you can just start, say something to open the session and introduce Ken Harris.
Yep. Okay. Just 1 second. I have everything here on screen. Okay. So, second.
Martin is also here.
Okay. I'm ready to start.
Okay.
Good morning, good afternoon to everyone. Welcome to the 8th session of the International Conference, Bamboo, a very sustainable construction material, and the 3rd World Symposium of Sustainable Biocomposite Materials and Structures. Today's session is Round Pole Bamboo Structures, Research and Innovations. I am your chair for today, moderator, and I'm David Trujillo. And our first speaker, who is already online, is Professor Kent Harries of the University of Pittsburgh, who will be delivering a talk on bamboo joint capacity determined by ISO 22156 complete joint testing provisions. So over to you, Kent, and yep, thank you very much.
All right, thank you. I'm going to share. Like every good Zoom call, I will tell you what I'm doing. I'm going to share my screen. And then I will do the mandatory, can you see my slides? Oops, that's actually wrong. Hang on.
Yes, I can see them.
Let's start at the beginning rather than the end. All right, so we're in slide mode. So there's my mandatory question. Close up that little box and we'll get started. Okay, we're going to get started today and be talking about bamboo joint capacity by complete joint testing, the provisions of 22156. And so we're going to jump right into the new or the new-ish design standards and talk about some of the implications of these and really show a process rather than the data. The data that I'm going to show is not that important. It's really demonstrative. What we want to show is how we go about this process. So I think at this point, hopefully most of the people online are comfortable and recognize that there are a suite of bamboo standards permitting the structural design of round column structures. And of course, they start off with 19624, the grading standard, a method of, or again, a procedure for grading bamboo. And David has been doing a lot of excellent work in really demonstrating how this can be put, can be implemented. We, of course, have the 22157 document, which talks about physical and mechanical properties, and these two will go together in using grade determining properties and what have you. And then we're going to put both of these together and use them to design our structures under 22156. And 22156 is really what I'm going to be talking about today. Just to bring everybody up to speed, 22156 is a relatively limited document. It's limited to 1- and 2-story light frame type construction, so residential, small commercial, and so forth. A roof limit of 7 meters, which is relatively typical, and so where the primary load bearing structure is actually made of round bamboo, and so this is the standard that we're going to be talking about. Let's zoom into that standard a little bit, and we find Chapter 10 addresses joints and splices, and it does so in a little bit of a different manner than we sometimes see in other types of engineering structures. We look at the nature of the force transfer between bamboo elements. And so we have a joint that may be actually made up of, or that is made up, of multiple connections. And each of those connections may have combinations of force transfer associated with them. In addition, Section 10 addresses issues of stiffness, ductility, and the resistance to splitting. And so this is what I want to get to today in a very simple fashion, is talk a little bit about these joints and how we may be able to design them. So if we look a little bit deeper into Section 10 of 22156, we find that there are some prescriptive guidelines for some relatively well understood joint types. And these would be then based on material properties or potentially grading. And so just as an example here, we talk about dowel bearing capacity.
To participate in simultaneous.
Hello, someone seems to have their microphone off.
Yeah, can we?
Thank you.
Okay, sorry about that. Well, I'm not sorry, it wasn't me. You guys can hear me again, right?
Very well.
Okay. And so as an example of dowel bearing capacity, we do have prescriptive guidance. And if you actually apply these, as a few people have pointed out, these end up with very conservative results. But of course, at this point, this is sort of this is a version 1 code. There are certain things that that we need to be a little bit conservative on until we really have a little bit more of an established code. Chapter 10 goes on. There we go. And references sort of a useful appendix, an informational appendix that looks at a number of rather conventional and in some cases a little bit non-conventional types of connections for bamboo. This is not really to say how you go about doing things. It is a bit of a roadmap. So if you're using a particular type of connection, here are the clauses. Here are the parts of the code document that you really should be looking at. And so it's informational in that sense. And so these are useful. But what one finds when one's designing connections, as we know, bamboo connections are bamboo, the science behind bamboo connection design is quite nascent. We find that very often either we end up with very conservative designs that are very difficult to implement, or we just simply don't have a prescriptive means of design. And so we need another tool. And that should be, and of course we need that because the potential number of different connections types of connections are almost infinite. We can have some very simple connections that might be appropriate in a vernacular sense. And of course, we've probably all seen some very complex connections, machined connections and even 3D printed connections and what have you. And so we need also a tool that can address all of these types of challenges that we have for connecting round members to round members, which is not exactly the easiest thing to do. So my slides are not moving forward. There we go. I think my keyboard died. What we have in the document then is a means of prescribing connection capacities, design capacities that we essentially call design by testing or complete joint testing. And so we can determine design properties based on full-scale complete joint assemblages. These would have to have essentially the same geometry, fastener elements, details, and so forth of the connection that we're planning on using in the field. The tests, then we give the guidance on how to do this. The tests are carried out essentially in accordance with ISO 16670. The properties are then determined in accordance with the technical report 21141. And then finally, we can determine characteristic values in an appropriate manner, and we cite 12122 in this context. And this is then design properties by complete joint testing. You're not going to take this approach if you're building a single structure. It's not going to be a rational approach, as we see. This is really, as we're going to see in a second, this is really aimed at these situations where we are building a large number of structures, where we're going to have, let's say, a roof truss system that we're going to duplicate thousands of times, or a wall frame system that we're going to duplicate and erect thousands of times. This is a way of determining the capacity of these particular elements rather than actually having to look at internal stresses in every case. And so there's a process. There we go. And I just need to get this out of my way. Sorry, I can't see what I'm doing. And we have a process that I'm going to take you through in this presentation. And so the purpose of this presentation is not to talk about the connection that I'm about to talk about, but to demonstrate this process. So the very first step up here on the top is we ask, can the joint be designed by prescriptive guidance? And if it can, we can certainly use the prescriptive guidance in 22156. What I want to talk about now is when we can't, or we don't want to use the prescriptive guidance because we feel it's overly conservative. And so we come into this next layer where we're going to use complete joint testing. And now we want to talk about what that complete joint testing is going to look like. So the first steps is we need to define the geometry and the material properties that we're using. the material properties, maybe through 22-157 testing, or potentially through grading, 19624 compliant grading. So we can go either way there, I think. And then we actually conduct the testing. So what I'm going to do is I'm going to take you through a very, very simple example. And it was intentionally a very simple connection. And it was also selected because it was a connection that we knew would not perform well in what we were asking it to do, because we wanted to make a couple of other points. So let's take a look at this process by example. And so we took a very straightforward example, a bolted fish mouth connection, where we have a fish mouth that has an internal drawbar. This drawbar is on the inside, and bolted to the back of what we'll call the column element, and the beam element is horizontal. These are then clamped into a test frame, the column horizontally, and the beam is cycled vertically up and down by use of an actuator in this case. And so we have a loading, as we show down here in the bottom of this particular image. This type of fish mouth is really not expected to perform well in terms of its moment capacity, but it will have a moment capacity because of the presence of the drawbar. So it might be something that in a very simple structure that we do want to understand what marginal moment capacity can we get out of this particular joint. And so we're going to go through this. And so this is the design of the test that we used. We have a couple details here that I think are really just interesting. And again, provided because this is the type of information that we would need if we were going through this process. And so we do document how the fish mouth and the connection was made. In our case, we used a large core barrel, really actually a nice tool for this. We document the dimensions of both the beam and the column elements. And so we have our diameter and our wall thicknesses, and the numbers in brackets are coefficient of variation. So a percentage or a ratio of the mean. We can see the connection being put together. We used some fender washers on the back so as not to crush the column wall when we tightened up this connection, and because it was tightened to a fairly large degree. And then we go ahead and test it. We have material properties, typical material properties for this particular material. It is guadua. It's a relatively moderate diameter guadua. Moisture content, density, all of those nice things that we would want to report. And the one I'm just going to draw your attention to, because I'm going to come back to it, is compression strength of about 43 MPa. And these are average values now. And the coefficient of variation, relatively typical, relatively high as well. And so now we go into the testing. And again, this is what we're demonstrating. So if we look at 16670, it's a process. We have a displacement load step relationship, which we need to follow, that's prescribed. From that, we develop a backbone or a hysteresis relationship for the connection. And from that hysteresis, we draw the backbone. That red dotted line then becomes our monotonic curve. And so if we take a look at the data from our particular test, we have applied force vertically, displacement horizontally. Again, we're testing in reverse cyclic behavior. So as the actuator pulls up, we're on the positive side up here in the upper right quadrant. And as the actuator pushes down on the negative side. And for those of you familiar with this kind of testing, we have a really nice pinched hysteresis behavior. 3 cycles at each displacement, with the cycles decaying a little bit. And so we have these plots. And in this particular case, we tested 20 assemblies, and this just happens to be one representative one. The envelope curves are then plotted, and just for convenience, I plotted the positive envelope in red and the negative envelope in blue. And what I'm going to do for all the rest of the plots, I'm going to flip everything up to the upper right-hand quadrant. The positive and negative aspect isn't particularly important. So we're going to move everything up into the upper right-hand quadrant, the red and the blue. So we've done the testing. Now what we need to do is determine the properties of these envelopes. What are the properties of my connection? And so here we look to the technical report 21141, and we have various means of calculating based on this backbone curve the joint stiffness. And so if we have an essentially linear portion, we have a joint stiffness. If there's an initial slip, we account for that. If there's initial friction in the joint, so different joints will behave a little bit differently. And similarly, a bilinear behavior. And in general, what we're going to do is we're going to find that stiffness as the secant stiffness now between, and rule of thumb is 40% of the maximum and 10% of the maximum. It doesn't have to be that, but that's the guidance. In addition, then, so we find the initial stiffness, in this manner. We then find the post-peak stiffness, or based again on the nature of the curve that we see. So is it a bilinear curve, in which case we just draw a secant having a stiffness of K sub P. If it's a degrading curve, we use the 1/6 of the elastic stiffness. We can use secants and offsets down here with degrading curves as well, or more of a typical offset method if we're looking at dowel behavior. In the case of this particular study, we used the bilinear approach. Most of the data was fit bilinear very well, in which case we have our rules for finding our yield point. We have our initial stiffness K sub E. We extend our post-peak stiffness backward until it intersects with K sub E, and we define the yield at that location. All of this is part of 21140. And so just an example, so I showed the blue backbone curve previously. I'm plotting it in the positive quadrant here, but we have then all of the values that we need. We have the 40% of the maximum force, 10% in order to find K sub E, this red dotted line. We fit K sub P on, fits very nicely, nice bilinear behavior. Extend that back to find our yield point, and we have all of the data that we now need to move forward with. And so again, doing this to show the process, there is a data reduction process that has to be documented when we're doing this complete joint testing. And this is just simply one example. Now, keep in mind, I've got 20 tests. I've got 40 backbone curves, 20 positive, 20 negative. And that brings up the next question. I need to look at my data and determine, first of all, does it make sense? But secondly, in my particular case, this particular joint would be expected to behave symmetrically, where positive and negative behavior would be the same. If that's the case, we actually have 40 backbone curves. You could also imagine a joint geometry which is non-symmetric, where it's going to have a very different positive and negative capacity. That being the case, we're going to have 20 positive, 20 negative. And so we want to test this hypothesis. In our case, particularly, we want to see that if we can treat both positive and negative together. And so we do very simple statistics, an unpaired t-test, to compare the positive and negative cycles, the 20 positive, the 20 negative. And sure enough, in terms of all of the capacities that we're looking at, the positive and negative cycles are statistically the same. And so we do have 40 data points. So that actually is kind of nice and helps us out a little bit. It also confirms our hypothesis that, of course, this connection should be symmetric, and it is. If it weren't symmetric, we might want to look at a systemic error creeping in and look at our test setup. So now we've got to normalize our parameters. It is not appropriate, typically, when we're looking at bamboo, unless we have very, 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 very tight control, to simply look at force and displacement. We want to look at moment, rotational stiffness, and stress, because, of course, these are affected by the dimensions both of the test setup, the length of the beam, and the dimensions of each of the elements. And these vary. It's bamboo. So we're going to normalize our data in terms of moment, rotational stiffness, and then ultimately extreme fiber stress. And with that data now, we want to look and determine what is the statistical does this data fit a normal or a log normal distribution? This is an important step, and I've seen it left out in some types of studies. When we go to determine characteristic values using conventional means, ISO 12122 or ASTM methods or what have you, there is a presupposition that we have a normal or a log normal distribution. And if we don't, the calculations of characteristic values using these tabulated values or very simple equations is incorrect. And so in this particular case, I'm just showing the distribution, the statistical Z-score versus the two moments, the yield and the maximum. And we see a very nice normal distribution. And we actually do see one outlier data down here at the bottom. So we had 40 data points. And so our final data will be actually work with 39. We do have a statistical outlier, which wouldn't be surprising in a bamboo test. And so now we can put all of this together. We look at both our applied forces and moments, so F max and M max, yield, Fy and My, stiffness, so Ke is the observed stiffness, the load versus displacement, K theta, the rotational stiffness, and then finally the extreme fiber stress, which I'll come to in a second. We can look at their averages, we can look at their coefficients of variation, and we notice as we normalize the data, we get a small improvement in each case, as we'd expect, because we're normalizing out the effect of comb diameter and wall thickness. And then we determine our characteristic value. Now this data, as we show here, here's all 40 curves, huge scatter, as we might expect from this type of connection. It's really not a moment connection. The red line is a best fit through all of the envelopes, so an average curve if you wish. The blue line in this case would be our characteristic value, assuming that we're using our 5% at 75% confidence. And so a very, very low bound, very, very poor moment capacity for this connection, which is probably what we would expect. And so that's the methodology that we would do for complete joint testing. Just then, sort of as some observations, I wanted to look at this particular test and the bolted fish mouth that we did test. After all, we have 40 data points and we may as well look at them. So our test setup, we actually pre-compressed or used the eye bolt to draw a fairly large force, 8,500 newtons. This was determined using a torque wrench. And so if I look at the compression force in the beam element, that's about 5.5 MPa if we take our average values. As we start moving this back and forth, we have different types of behavior. We have dowel bearing type behavior, particularly at this location. And it's interesting because if we look at our ultimate stress condition, we would have tension in the eye bolt, compression at the top or bottom fiber of the joint, and opening at the opposite side. And when we calculate the extreme fiber stress, in this particular case, we had about 36 MPa, and that's where I want to bring you back. The average capacity of this particular bamboo was about 43 MPa, so we're right in that ballpark. We actually designed a relatively efficient joint for what that bamboo can carry. Now, this is not an efficient means of resisting moment, largely because we have such a small lever arm that we can't get much force out of this, even with a relatively large stress. So we can learn a little bit about our joints as well. This issue is really an aside for this data. So in conclusion, hopefully I'm on time here. Demonstrating a complete joint testing program and all of the steps involved. And so designing the test to mimic appropriate use, looking at the statistics of those tests, both checking our hypothesis, is it symmetric? Do we have systemic errors? Normalizing for geometry, determining whether we have normal or log normal distribution in order to calculate characteristic values. Of course, if we have different distributions, we can calculate those characteristic values. We just have to do it a little bit different manner. And so again, this particular presentation, the bolted fish mouth joint is not important. The intent was to demonstrate the complete joint testing process of clause 10.2 of ISO 22156 from start to finish with this nice little flow chart. And what I would do, I would direct those of you who need to look a little bit deeper at this. This was published recently in the brand new Elsevier journal, Advances in Bamboo Science. I would encourage my colleagues to support this journal, because I will tell you that if we don't get a lot of good quality papers in this journal, Elsevier will pull the plug after a couple of years. So consider sending your data to this journal. And with that, I think I'm on time.
You are, Kent. Thank you very much. That was a brilliant presentation. I enjoyed it very much. I have lots of questions, but I see that the Q&A session is at the end. So I suppose we'll have to just park them there. Though we do have a cancellation, so maybe we could do an interim Q&A session before that. Firstly, I want to apologize to you, Kent, for not introducing you properly. So
everybody knows me
properly. I'll introduce you properly all the same. So Kent Harries is a professor of structural engineering and mechanics at the University of Pittsburgh. He received his doctorate from McGill University in 1995. Harries' researching interests include the use of non-conventional materials in civil infrastructure, ranging from FRP to bamboo. Harries is a co-author of over 320 peer-reviewed articles and 3 books. He is senior editor of the Journal of Construction and Building Materials and is co-editor of the book Non-Conventional Vernacular Construction Materials. Harries led the effort to revise ISO 22156 bamboo structural design. Harries is a fellow of the ASCE, ACI, IIFC, and is a professional engineer in Ontario, Canada. I also need to introduce someone who is joining us today, who is Mr. Durai Jayaraman, the Global Program Director of INBAR, who is in today's session and will be talking to us all at the end of today's session. Finally, I will introduce my co-chair, or co-presenter, who is Cristoforo De Martino, who will be now introducing our next speaker. Thank you very much, Kent.
Thank you, David. Over to you. Thank you very much, Kent, and sorry for our late chairing. We will try our best to stitch on the program. So the next speaker is Dr. Xin Zhuo from Zhejiang University. He is my colleague. He's an associate professor and is the director of the Construction Technology Research Laboratory in the College of Civil Engineering and Architecture. And he has spent more than 2 decades on researching the construction technology of complex shape structure and pre-stressed special steel structures. The title of his presentation will be the Novel Low-Rise Bamboo Column Structure Building System Composed of Prefabricated Frame Units. The stage is yours. Can you please share your screen so we can check if we can see your screen?
Okay.
Please.
Thanks, moderator.
That we have 20 minutes, so let's try to respect this time. Thanks.
Thank you very much. Good morning, good afternoon, good evening, everybody.
Zhuo, we cannot see your screen. Can you please share your screen?
Wait a moment. I will share my screen to you. Wait for a while. Share my screen. Can you see my screen?
Yeah, please go ahead.
Okay. Hello, everybody. Today I want to deliver my presentation in Chinese to more fluently and accurately introduce our innovative research works and my perspectives on the development of the bamboo building industry. My speech in English has been sent to the organizing committee. The interpreter is invited to participate in simultaneous interpretation. 今天为了更流畅而准确地介绍我们
In order to be more smooth and accurate to introduce my viewpoints, I will do this presentation in Chinese. We have simultaneous interpreters to help with the interpretation. This is the background of my research. Bamboo palm is a type of perennial plant and also grow very rapidly. Traditionally, we had already bamboo construction, but due to this poor structure, people say bamboo construction are for the poor people due to the instability. So without any technological modernization, we can not make bamboo resources a market resource. We have bamboo scrimber and also other types of bamboo palms. Bamboo is very environmental friendly without using chemical adhesives. And for the market, it's very cost effective. Most people tend to purchase the most cost efficient products instead of those products with the best performance. So when we develop bamboo palm structures, we should focus on reduced cost, better texture, and which can meet consumer demand. We believe bamboo palms are more suitable for 1 to 2 story low-rises buildings. Let me briefly review on the contemporary bamboo palm structures system. At the Expo 2010 in Shanghai, there were 2 outstanding bamboo structures. One is Vietnam Pavilion built by Mr. Wochong Neha and the German-Chinese home designed by Marcos. These 2 buildings, which are designed very differently, displayed 2 structural systems of current original bamboo structures. There are many varieties of bamboo palm arch structure system, including planar bundle palm arch structures, cross palm arch gel structures, cross bundle palm arch structures. The construction of contemporary bamboo structure has been greatly aided by these remarkable structures. A large number of emerging bamboo palm grade joints have been developed in recent years. Back to China, in recent years, there have been many bamboo palm structure buildings developed in China. However, we noticed that while there were numerous bamboo palm arch structures, there were very few bamboo palm grid structures. We believe the major cause is that fabricating multi-directional joints is too challenging. It's difficult for the business to manufacture it. But if they try to purchase it from the market, it's very expensive. Bamboo industry specializes in creating bamboo arches. So if they can produce bamboo arches themselves, they can generate higher revenues. Having said that, the bamboo palm arch structure system still has a cost issue because currently we are mainly depending on the artisans manually to baking these curves by fire. It's low productivity, higher labor cost. As a final result, bamboo palm arch structure having no cost competitiveness over timber structure, which is very unfavorable for the development of bamboo buildings. We know that bamboo and timber are both bio-based materials. So if bamboo does not have the cost advantage, why should customers select these bamboo because it's a lack of mechanical qualities comparing to timbers. So we need to maintain the cost. There are two types of bamboo column structure systems. High expenses are mostly a result of hand-bent bamboo tubes and customized multi-directional joints. It depends very much on the labor and also the skillfulness of the labor. So we cannot standardize the construction results. On the contrary, the bamboo column grid structure is having the strict column and the low cost. But the disadvantage is to make multi-directional joints, lack of universality. So what our Zhejiang University is trying to combine the advantages of these two types. We use a straight rod plus bolt because a straight rod and bolt are both less expensive. But can we directly combine the two structures? It's impossible, so we have to come up with an alternative solution. Next, I want to move to the innovative frame unit bamboo column grade structure system. In 2017, I follow my PhD supervisor, Professor Dong Shilin. We jointly promote the bamboo multi-column spatial grade structure system and got the patent. I'll give you a simple example. We all know that the grade structure at the very beginning, we would start with the axis and the geometry sizes. The key to the construction is the spatial layouts of the connections and joints. What we are doing here is to make the initial complicated three-dimensional connection to a straightforward one-dimensional connection. So you can see this is a very simple structure. No matter how complicated the shape of the construction, we do not need multiple dimensional connections. We streamline the 3D connection issue into 1D connection. There are two-step processes. The first is fabricate the component in the factory. Second is on-site construction. For the on-site construction, first we drill the holes first, and then connecting triangular frame by bolt to form the whole structure. You can see this is very easy to construct, very easy to learn. For the workers, if we teach them to do one triangular structure, they can repeat the whole process. For the whole construction team, if we can teach them the first project, then we can have hands-off attitude, and we just provide them the data, and they would follow the exact steps as the first project. Very easy to learn. Since 2019, we have created structures in the hyperbolic paraboloid. On the left-hand side, you can see this structure. I want to thank INBAR for your support and trust. And after that project, we completed the cylindrical and spherical structures, which shows that these structures are quite suitable for the traditional steel structure constructions. But I'd like to draw your attention on these stress transition routes. You can see on the left-hand side is a steel tube. On the right-hand side is the bamboo column. With the same wind load, the right bamboo column structure deforms differently than the left steel structure. Of course, we need further study on the internal forces. Having said that, we can still see the stability of the bamboo column structure. Currently, we already completed from 0 to 1. But how can we make from 1 to 100? This is a remaining issue. To make these bamboo structure more beautiful, cheaper, and environmentally friendly, we decided to change the combination method. For example, some of these constructions, they use 2 bolts. Some use 3, some use 4. It depends very much on the inner forces. This is the first consideration. Second consideration, if there is any large span needed, this is for the 2022 Hangzhou Asian Games for the athletes and journalists reception center. Because this is a contemporary construction, in order to save the cost and also to promote environmental friendly concept, they decided to use bamboo. We have 2 alternatives provided.
The second one is a spatial grid truss to increase the structural rigidness so we can have a larger span. But unfortunately, we know that due to the COVID, this project was delayed until next year. So we hope that in future, the other countries or other cities, if we want to have a test of the structural design, we can test it in the field. Another thing is the durability issue. For a bamboo structure, I think the biggest question is
Hello? I don't know what happened. I think, Zhuo, can you hear us? I think that we lost him. Still connected? Let's wait 1 minute if he can reconnect, or we will move to the next speaker. David, what do you think?
Yeah, let's give them a couple of minutes and then we'll move to the next speaker.
Yeah. Unfortunately, this is the problem of online meetings, right? Sometimes people are disappearing without any willing.
Yeah. Well, our next speaker, who I'll introduce while they reconnect, is Visalakshi Palakokul, a professor of Mahindra University. She will be presenting a development of high-capacity fiber-reinforced bamboo composite structural members. I don't have
I
a
think
formal
that
introduction
David,
for that.
Shin reconnected. I don't know if you want to give him 1-2 minutes to complete.
Yeah, absolutely. I was just making sure
Yeah,
there wasn't any dead time.
Chuo, do you want to complete very fast? Because unfortunately the time is almost finished for your presentation. Sorry? This means continue?
His microphone is off.
Yeah, you are muted. We cannot hear. Chuo? You are muted. You are still muted. Chuo, you are muted. And unfortunately, the time is very limited. We have to move to the next speaker. Can you hear me?
Okay, mode.
Yeah. Please complete your presentation is 1-2 minutes. I know the technical problem, but we have to respect the time, okay?
Sorry. Oh, okay. Can you see my screen?
现在能看到
You can complete please in 1-2 minutes, okay? Because unfortunately, the
1-2
time...
minutes.
Okay.
Okay. Next page. 说一下这个复杂形体结构。
So this is more complex structure. This is the bird's nest. Everyone knows this. And this is a curvature design. But the issue is that in the structure, every component is bespoke. So the construction, the manufacturing, processing are extremely challenging. If it's a timber, and if we have a curvature connection, then you will face a similar challenge. Every piece has to be bespoke. The 2019 Swatch headquarters in Switzerland is using a similar design with timber. You have to very precise when you make such structure. Everyone wants to make a very beautiful, magnificent structure. Modern technology allows you to make such complex structure, but can anyone afford it? Is an issue. And some university students, when they participate in the design context, they use all types of free surface. Yes, geometry is no longer an issue with Rhino and other designing tools, but manufacturing and installation and construction are the issue. Here, I'm showing you a 3-dimensional calm arch. This is a rendered version. It looks magnificent, but now you can see it doesn't really shine. It's not that the bamboo constructors don't have the handicraft. It is difficult to do it manually. And can we use, we can having a gym. We have 2 models. If we have the calm, we can have a sloped. We also can have a free curvature surface. And we have the same number of triangles here, but one is too common. The other one is very eye-catching. And so one is steel structure, one is timber structure, very beautiful. But the issue is that the manufacturing, the components, installation, and construction are extremely complex. If we use the triangular bamboo structures, manufacturing is very simple, although the structural design can be very challenging. So it can really reduce the overall construction cost. And the final one is quadrilateral frame unit for residential buildings. Even if we have a high rise, people still want to use wood or bamboo to have interior decor of the floor and the walls. In many countries, we have like a 2-story low-rise buildings made of wood, and structure and the interior decor are two in one. No need for secondary interior decor. And inside China, more people prefer to have a natural material for construction. But now every year, a lot of timber is relying on import. Bamboo is in oversupply, so we can use bamboo to replace timber. It can really deal with the scarcity of timber supply, but we just don't have a good way to do this. We're using quadrilateral frame unit as a structured unit. It is like modular, installable in situ, and the connection method is was explained before. And it is quadrilateral frame. One is triangle. Of course, they have different mechanical properties. We just want to offer a second choice for people. If you really like timber or bamboo structure for a construction project, you can have a good value for price, lower cost alternative choice. Our student, they also designed and built a 1:0.5 ratio miniature building, proving that the structural and construction methods are fully actionable, workable. And depending on your comfort need, you can have an insulated layer in between the panels and waterproof materials. And also we can work in the B&B hostel, and we have some structural design to use some block-based smart calculation algorithm to have a fast programming and use figure out the spatial dimension layout of different building blocks to have a high efficiency design. Final conclusion, the engineering practice verified by the viability of the prefabricated frame-based low-rise bamboo column structure building system. It is a low technology intensity, simple to learn and spread. Second, triangular frame unit, bamboo column grade structure is most cost-effective for complex-shaped buildings. Low-rise bamboo column structure house has enormous market potential as long as the quality can meet expectations of modern people and the price is affordable. It has a huge market potential. And number 4, replacing the decayed frame unit in situ is an effective way to prolong the service life of the bamboo structure. Okay, I finished. Thank you very much.
Thank you for your presentation. As you know, we will move to the question and answer session at the end. David, please go ahead. I think you introduced the next speaker, but you can reintroduce again.
Yes, I will reintroduce it. So our next speaker is Professor Visalaski Talakapul, who is a professor at Mahindra University. Unfortunately, I haven't been supplied with an introduction. Is Visalaski here in the call? Her presentation is development of high-capacity fiber-reinforced bamboo composite structural members. Professor Talakapul, are you here? Hello? Okay.
Hi, David. I think he's not here.
I think she isn't either. No, that's fine. So I'll go with my next speaker. The next speaker, who is Xin Miao Meng, who is a lecturer at Beijing Forestry University, who has a presentation of ecologically self-anchored FRP bamboo composite anchor bolts, concepts and experiments. Dr. Meng graduated with bachelor's degree in civil engineering from Chongqing University and his PhD degree in civil engineering from Tsinghua University. He became a lecturer in Beijing Forestry University in 2017. His main research focuses on the mechanical behavior of FRP bamboo composite structures steel timber composite structures, and wooden-based sustainable construction materials. He has served as an editor of national standards and 2 CECS specifications. He served as a junior editorial board member of the Journal of Sustainable Structures. Dr. Meng, please start.
Okay, thank you. Thank you,
And just a
Chairman. Can
reminder,
you see
Dr.
my
Meng,
slide?
I can, and just to remind us previously, let's try to stick to time. Thank you very much.
Okay, no problem. Okay, thank you, Chairman. Dear everyone, I'm Xin Miaomeng from Beijing Forestry University. It's my honor to present my research work. The topic of my presentation is ecologically self-anchored FRP bamboo composite anchor bolts. Its concepts and experiments. Okay, it contains 4 parts. First is background. Okay, in the last 3 decades, China has planted lots of trees to prevent soil erosion. Due to the robust plant root system, the shallow landslide can be restrained, but when it comes to a heavy rain, the landslide will occur. So in this regard, we need anchor bolts to protect the slope. In addition, the anchor bolt could be used in lots of applications as shown in this figure. And it has been proved that the anchor bolt has been is effective enough in ground anchorage application. And generally, the anchorage bolt can be divided into 3 types, including mechanical, bonded, and hybrid ones. And it mainly carried on actual tension in soil slope. And we usually used the steel bar and some conventional materials to produce the anchor bolt, like steel, like wood, and bamboo products. In addition, some new materials has been explored in anchor materials like the FRP, MPR, and composite components. At present, okay, we want to use some green, ecological, and sustainable materials to reduce the carbon dioxide emission, and we also need to increase the ductility. In this regard, and we proposed a new composite anchor bolt. It's composed of FRP and fiber reinforced polymer and cell and bamboo materials. It has a self-anchor U-shaped end, and it also contained 2 kinds of grout materials. One is ecological grout, like the ecological concrete, and another one is the high-strength grout. And using this anchor bolt, we can combine the plant root system and the anchor and the FRP anchor composite bamboo anchor both. And we want the root can grow to the anchor bolt, and in this way, an integrated anchor slope, protection slope, can be developed once the root grow into the U-shaped end. And we also, for this new composite anchor bolt, it is from the CFRP, and the self-anchored structures has been studied in FRP applications. It could fully utilize the tensile strength of the materials. For CFRP, it has two laminated structures, like the non-laminated straps and laminated straps. And it has also been explored in the anchor bolt in EPFL. Professor Keller has used the CFRP, the CFRP multi-stripe CFRP end in the ground anchor. So the self-anchored use the U-shape and is already being explored in FRP materials. And another one is that bamboo is an ecological construction materials. It has very low energy consumptions. And also it has very short growth cycle, easy processing, and also high strength and lightweight. And another one is that we calculated the carbon emission factor for round bamboo. It was found that the round bamboo, the emission factor is very low compared to the conventional materials. And if we considered the carbon sequence traction, and it can be the negative carbon materials. And in the carbon emission factors, one most part for the carbon emission is that the thermal bonding process, like Professor Zhuo mentioned. And if we reduce this liquid natural gas, if we remove it if we replace this LNG with solar energy, we can reduce the carbon emission factor. We can decrease this a lot. And so we think bamboo is an ecological building materials. And another thing is that China has abundant bamboo resources, which helps to reduce the cost of the bamboo structures. And then we conduct a literature review of bamboo bowls. And we found that the bamboo bowls has been used since 1977, mainly in roadway support of coal mines and the earthside protection. Different bamboo materials had been explored, including strips, scraper, and engineered bamboo, also bamboo camps. And for the rigid structure, it is like the steel boat, and it is used on the ground side anchor height, including single wedge and multi-wedged end. And another one is that if we want to increase the anchorage, we can use the expansion shell in this place. And another one is that besides the wedged ends, the bamboo bowls can be designed as the serrated segments. And for the scraper bowls, it is very similar to the steel bowls due to the reason in both its strength and durability can be improved a lot. And also for the round bamboo camps, they can be individually used and also can be combined with the steel rebar as shown in the figure. They have been already applied in the earthen size. And next, I will introduce the self-anchored bamboo bowls. The U-shaped anchor bowls could be defined with the slope, angle, the thickness, and the diameter. And it can be achieved by two methods. One is the thermoforming, and another one is winding. And we, like Professor Zhuo mentioned, that we can use the thermoforming to make the curved bamboo can, but the temperature is unknown, and actually the carbonization of the surface cannot be avoided. So we want to improve the thermoforming process and obtain the suitable temperature range. We studied different thickness of the bamboo strips and applied different temperatures. And we also conducted 4-point bending test. We found that the flexural modulus changed with the temperature, but I think more microscopic research should be done to explain the relationship between the modulus and the temperature. We just find the trends, but we didn't find the role. Then we tried another way to make the U-shape, and it is a winding method. We use the bamboo strips and use the winding and use the FRP and to get the FRP bamboo composites. And we developed a method based on image recognition to design the mechanical properties of bamboo bowls, because different strips, the tensile strength of bamboo strips is related to the fiber of the bottle, the density of the bottle. And another one is that we conducted the tensile test for the bamboo strips and obtained the tensile strength for the bamboo strips. And we also defined the methods to separate the bamboo strips into different groups to design the bamboo bowls based on the mechanical requirement. And here's the relationship between the fiber volume fraction and the tensile strength parallel to ground. And then we conduct the tensile test for the bamboo balls. In this boat, the GFRP was just used as the coating. And we found that most of the specimens filled with a fiber rupture at the U-shaped end. And another one is that we also designed pull-after test. It was still under test due to the COVID-19. And but the theoretical analysis has been done. We divided the self-anchor composite boat into two parts. For the linear part, we built a model to predict the shear stress and the interface and the tension force. And we tried two models. This model is based on the half-space model and is based on the elasticity. And we can conduct the parameter studies to find the relationship between the elastic modulus and the shear stress distributions. Another method is that the bond slip constitutive model. We prefer, among these models, we prefer the trilinear model to predict the bearing capacity. And here is the Philip mode. We obtained the shear stress distribution at the interface through the whole loading process. And then we studied the relationship between the loader carrying capacity and the bond strength. And we found that we need to optimize the plastic performance to improve the capacity. And after the U-shaped anchor, as for the U-shaped anchor, we combined the thin shell model and the thick shell model to get the load distribution and the stress distribution across the section. But we know that for the thin shell model, because it didn't consider the thickness, so we don't know the stress distribution across the thickness across the cross section. But for the thick shell model, we can obtain the stress distribution across the cross section, but we cannot consider the friction at the interface. So here's the results. We can get the stress distribution along the boat and across the cross section. Then we combined these two methods together, and we found that here's the theoretical results. This is the experimental results. We found the results showed large deviation. So we think we need lots of tests to evaluate the accuracy for these two models. And we also conduct a finite element analysis and to verify the theoretical model. It proved that the effectiveness of the thick shell model. And here's some conclusion for the self-anchor balls. First, we found the temperature is related to the elastic modulus, and we found that we need to optimize the temperature for each thickness. And U-shaped anchor could improve the tensile, the loader carrying capacity for the anchor bolt. And we also studied the theoretical analysis based on the elasticity and the thick model, or the thick shell model or thin shell model. And we think that if we want to fully develop the tensile strength of the FRP and bamboo materials, we need design its slope angle, its thickness, also the diameter of the inner diameter of the bolt. So finally, in the end, we draw two conclusions. The first one is that we proposed an ecological self-anchored FRP bamboo composite anchor, but we also need more tests to verify our concepts. And we think it can provide enough load carrying capacity and durability, because we want the FRP to provide the durability. And if the road growing into the anchor bolt, and we think we can build an integrated slope protection system. And we conducted some theoretical study and experimental test and some finite element analysis. We found that the bearing capacity of U-shape is considerable. And that's all my reports. Thank you.
Thank you very much. That was a very interesting presentation, Dr. Meng.
Thank you.
Now, I'll pass you over to my co-chair, Cristoforo.
Thanks. Okay. So the next speaker is Professor Luisa Molari. I think I've seen her. Can you share the screen in the meanwhile when I'm introducing? Fine. Professor Luisa Molari is an associate professor of strength material at the alma mater Studiorum University of Bologna. She's a structural engineer with a PhD in structural mechanics, and she teaches theory of structures at civil engineering and architecture students. And the focus of her research is on natural materials for construction, in particular bamboo, straw, and reed, and for their use in a structural context. The title of her presentation is The Effects of Mechanical Properties of Bamboo Treated with Fire. You have 20 minutes, Luisa. The recommendation is please try to respect the time. Thanks. And
yes, that would
the stage is yours.
Thank you. Thank you so much, Cristoforo. Thank you for your introduction. And yeah, I'm going to talk about the effect of on mechanical performance of bamboo treated with fire. Okay. So, as we all know, bamboo, as all the natural material, is susceptible to degradation. And so we have to treat it. And among the non-chemical treatments, the heat treatments have attracted increasing attention. The bamboo heat treatments consist of subjecting bamboo to high temperature in specific time, and the medium for this is can be several factors like steam, oil, air, or fire. And but generally, the heat treatments improve the dimensional stability and the durability, and this is why they're done. But on the other hand, the increasing temperature could reduce the mechanical properties. So we have to look at it and to show what happens to the mechanical performance of the culm. What the Italian and crafters and are usually doing is to use this abura nuki traditional treatment. This is a Japanese treatment, and it's made with a torch that remains at 10 centimeters of distance with respect to the culm, and the culm is constantly rotated, and it's constantly rotated, and the torch the torch is moving when there is a change in color and there is a swelling of resin in the culm. And after this treatment, usually the culms are dried for 10 days or for some days, usually in the sun. And so our question is, what happens to bamboo mechanical performance when a culm is treated in this way? So to to answer this question, we took a culm, and this is part of a study of the mechanical characterization of Italian bamboo. So we took Italian bamboo of Philostachys viridis species from a central part of Italy, is from Macerata, and it was provided by Polyedra Association, that is an association that are using bamboo in the social context. And so we took these culms, and we took two parts of the culm, a bottom part from 0.5 to 1.5 meter, and then a top part, from 2.5 meters to 3.5 meters. And we performed some tests on this two part of culm, treated and untreated. First of all, we looked at the density and at the moisture content, and what we saw is that the density is slightly higher in treated bamboo in respect to the untreated, but not statistically significantly higher. So we passed from 680 kilogram over a cube meter to 740 kilogram over a cube meter. Then we performed some mechanical tests to see how the treatment was influencing the mechanical performance. So we did compression test, tension test, and bending test. The tension test and the tension test and the compression test was we followed the ISO 22157. Even if in the tension test we do not put the tabs to increase in the cross section in the anchorage position. And for the bending test, we followed the new Italian standard, that is the UNI 11842. And for the measure of the deformation, we put a strain gauge in two directions for the compression at the formometer for the tension, and strain gauge in the bottom part of the specimen for the bending test. The bending test, as I already said, follows the new Italian standard, and actually we did only the test on the specimen with the external part on the bottom of the specimens, because we wanted to test if the surface treatment was doing something or not. So the results for the compression test. What we saw is that for the compressive elastic modulus, actually we do not see a lot of difference here. In green, the untreated culm, in yellow the treated ones, and in light color the part that are from the top of from 2.5 meters to 3.5 meters, and in the darker color the one that are on the bottom part of the culm. So what we can see is that basically there is no differences in the stiffness of the there is a differences in some differences in the average value, but not statistically significant in the distribution. And for the compressive strengths, we can see more or less the same things, because if we compare the darker with the darker and the light color with the light color, so the part that is from the bottom and the part that is from the top, each other, I mean, one with its correspondent specimens, we do not see much difference even in this case. What we see that is quite different, the only thing that is quite different between treated and untreated samples is the Poisson ratio. And we did the Poisson ratio is the ratio between the circumferential to the longitudinal deformation of the specimen. And what we see is that for the untreated, we have all the specimens that are in a much closer range in respect to the one of the treated samples, and this could have an explanation. I will come back to this in the following slides. The result for the tension test, again for the elastic. For the elastic modulus, also in tension, there is not a lot of differences in the. If we look at the distribution, we do not have a significant difference. And the same for the tensile strengths. Here we can see the slightly difference between as we know as it was expected from the bottom to the top. So in the top there is a average value that is higher than on the bottom. But if we compare bottom with bottom and top with top, we do not have significant differences in the strength. We can, for the bending test, we have only the bottom part, because we did only for this part of the culm the test. And what we see is that there is again more or less the same behavior in stiffness and in strength. Here we for the specimen that for the specimen after the bending test, we did micrographs, micro pictures with the ESM, with the microscopy, and we see that that for the treated samples we had a sort of texture. There are some cracks between the island of the fibers and the parenchyma cells, and this is quite. I hope that you can see, but there is evident the differences between the two, and this is something that could explain also the differences in the Poisson ratio, because we do not see some damage in the direction of the fibers, but we can see a damage in between fibers and the parenchyma. So this could bring to more or less the same behavior in the direction of the fibers, but something different in the direction orthogonal to the fiber itself. After that, we have thought, but with this treatment could bring a advantages or could be a disadvantage for when the culm is subjected to UV ray. And to answer this question, we took some samples, 11 identical samples, identical in the sense that we took from the same portion of culm. We took these samples and from treated and untreated culms. And we posed this stick of culm like this under the irradiation of UV ray, and then we tested these aged samples, treated and untreated, with a bending test, a 4-point bending test, as we saw previously. And we radiated the samples for different duration, from 0 to 360 hours, and we tested at bending to see if the mechanical characteristics were influenced by the UV ray, but also by the treatment, the previous treatment before the UV ray irradiation. What we did is also, because when the samples were under the UV ray irradiation, there was a temperature that was around 40 degrees. We put some samples of the same portion of the culm, so more or less identical, in a oven with 40 degrees of temperature constant for the same duration of the irradiation, to see if something changes. So to, in some sense, separate the two effects, the effect of the temperature and the effect of the UV irradiation. And what we saw is this. These are the bending strengths, and what we saw is that the treated sample, the untreated sample, the natural one, basically has had a slightly increasing of the strength and then a decreasing on the strength. But after 360 hours, we do not see much differences in the strengths, in the bending strengths. Again, this is something that is something that is related to the properties in the longitudinal direction, of course. What we see for the treated one is that we have this increasing strength that is shifted in respect to the treated one, and we have then we have this degradation, but is slightly shifted in respect to the untreated one. And what we see for the specimen that are only that remain only in oven at 40 degrees of temperature, basically nothing happened to them. So the strength is more or less on the same values. So in conclusion, we can This is a study for a specific treatment that is usually performed in bamboo culms, and what we can see is that the mechanical performance along the direction of the fibers are not influenced, and from the microscopical pictures seems that the performance on the orthogonal direction could be influenced, and we should investigate this because this is something that can be added to this knowledge. We can also say that the UV radiation till 360 hours do not influence the mechanical performance in treated and also in the untreated, but also in the treated ones. So the treatment makes no disadvantages and on this, and again the mechanical performance on the circumferential on the direction orthogonal to the fiber should be investigated more. Okay, I'm finished. And also, okay, just last thing. Also, we need to go further for the irradiation, for the duration of the irradiation, because we started to see a slightly damage on the mechanical performance.
Thanks for your presentation, Luisa. We can move to the next speaker. Please, David, go ahead and introduce the next speaker. The next presentation will be 10 minutes.
Thank you, Christopher.
Time. Yeah?
Yeah, that's correct. The next presentation is 10 minutes, and it is from Miretu Tadesse from Bahir Dar University. Miretu's presentation is called Bending Stress Prediction of Oxytenathera abyssinica, bamboo based on geometric section. Over to you, Miretu.
All right, sir. I'll start. Okay. Is that audible? Shall I start? Shall I start, sir?
Yes, you can start, please. I can see your presentation. Right. Thank you very much.
Okay. I'll start my presentation. Bending stress prediction of Oxytenathera abyssinica bamboo based on geometric section. I'm from Ethiopia. So let me introduce the chapter. As we all know, there are various species of bamboo. So among these,
sorry to interrupt you. Sorry. I think your presentation would look better if you click on the presentation button.
All right. This one. Now it's
that's
okay.
Much better.
Okay.
Thank you.
Okay. Okay. So as we all know, among the many species of bamboo, there are two indigenous species of bamboo in Ethiopia, namely the Oxytenathera abyssinica and the Yushania alpina. The Oxytenathera abyssinica bamboo, it covers 80% of the bamboo species and around 850 hectares of land approximately, and the highland bamboo or the Yushania alpina bamboo covering the remaining 20%. And the Oxytenathera abyssinica bamboo, the largest cover, and it's found in the northwestern part of Ethiopia, while the Yushania alpina is central and south part of Ethiopia. My research focus is on the Oxythenatera abyssinica bamboo. Considering the calm geometrical shape, these two species have different geometry. The Yushani alpina, it is 10 to 12 centimeter thickness, and it consists of a hollow calm. And it may, it has a height of a maximum height of 16.75, as previous researches reveal. While the Oxythenatera abyssinica bamboo, it has, it has a solid, semi-solid, and hollow sections. When you take 3.5 meter of this section, it consists of solid section from the bottom and semi-solid section at a certain height, and it consists of again a hollow section. But these sections, it varies depending on the age. I mean, when the bamboo at 2 or at the first and second year age, I mean, first year, 1 year and 2 year age, the semi-solid sections and the hollow sections is a little bit shorter, while consisting of less solid section. I mean, in a 3.5 meter specimen. So the mechanical property, considering the mechanical properties, of course, previous researches revealed that the modulus of elasticity, and modulus of rupture, it is 30 and 30.5% increment in both these mechanical properties. So my objective on this research is at what age the solid section of Oxythenatera bamboo at what optimum age, and to predict or to determine the age. And secondly, what is the concomitant or the respective bending strengths for the different ages. So having these objectives, applying the ISO 22157-1, a total of 60 columns were selected based on the cluster sampling method, and it will be dried, I mean, naturally by vertically stacking in the laboratory of Bardar University, Faculty of Civil Engineering Department, and it is kept until the moisture content is 11 to 30% is achieved. Then splitting is done through a splitter in the workshop, so that how much the solid section and the semi-solid section and the hollow section in a 3.5 meter bamboo specimen or beam is measured. Then this was the simple approach to determine how, depending on the age-wise portion of this, portion of the solid section, semi-solid, and hollow sections. So this is the area where the bamboo is collected, and in one of the region, we call it Methakal region. So as it is shown, the bamboo species, it's sketched as solid section, semi-solid, and hollow sections, and then it is clustered, it's categorized, and measurements have been conducted. And this is a simple, sketch how the cross sections look like when the bamboo at 2.6 meter is sample, solid section internodes, while here at 2.6 to 3 meters, how the hollow sections look like, and the cross sections are beyond 3.2 meters, having a hollow. So systematically, we have a solid section here it's a sample actually, and other lengths up to semi-solid sections LA, and the hollow sections within a 3.5 meter specimen. So the next step, a flexural, to conduct the flexural test, a test rig is prepared, and using a UTS machine, so that applying the load, we can, I will start measuring. So the results show that basically two mechanical properties was conducted: the compressive and tensile strengths according to the ISO 2021, sorry. So a mean strength of 28, 35, and 52 megapascal was resulted at the semi-solid, solid, and hollow sections respectively, an average moisture of 12 to 2% for 2 years age specimens, and there was a 3 and 8% compressive strengths for the ages of 3 and 4, and with the same moisture content in the 3 and 4 year age bamboos. And the tensile strengths is done. It's a dog bone shape that's based on the outer sections. I mean, it is tensile strengths 298, 146, and 112 megapascals for age 2 respectively is resulted, and the result is increased. It's 14 and 17% mean tensile strength was resulted for the age of 3 and 4 at the stated sections. The other testing, that's the main parts of the research, the bending test result. Here, as I mentioned earlier, the age-wise, the bamboo was categorized 2, 3, and 4 year, and bottom diameter and solid section length, as previously stated, and the internal length and the top diameter is, these are geometrically measured, and we have the ratio of the top end to bottom. Then the flexural strength and the mid-span deflection is measured. These results from the outputs are from the UTS machine. Then based on the statistical analysis show that the length of the solid section at age 4, where this is, sorry, the horizontal, the ratio of top to bottom diameter, and this is the length of solid section. So for 4 year, it's expected, I mean, it's an average of 2.8, 2.5 here for solid section length resulted at a diameter ratio of mean diameter ratio of 0.64. For H3, when the ratio of the top to bottom diameter is an average 0.77, while the length is less here, 2.6, 2.5 is resulted. The other one at age 2, here it's a 0.83 mean diameter ratio, top to bottom ratio, but the length of the solid section is below 2.4. So here from this result, we can estimate or see that a maximum of up to 2.8, 2.85 meter solid section length is available at age 4 when the diameter ratio is 0.64. And the other result from this research is the bending strengths. So the bending strengths versus the diameter ratio, so bending strengths versus bottom diameter. So the results in 3 specimens, 3 types of specimens are conducted, so that here shown that the result. Similarly, at age 3 and at age 4. So the final bending result values, the solid section is predicted linearly with 5.8D, 6.4D, and 7.2 times D for H23 and 4 respectively, with the statistical values in each sections. So here, the final conclusion that is resulted from the statistical analysis. So that's my presentation. It's a very short. I finalized in this way.
Thank you very much. That was a great presentation. I greatly enjoyed it. I have a lot of questions, but we'll leave them for later on.
All right.
Christopher, over to you.
All right. All right.
Christopher?
Yes, sorry, I missed your part because my connection was not good. Okay, I will announce the next speaker. The next speaker is CGA New from Hanwei Agricultural University. He got a Master of Forestry and Landscape Architecture of Hanwei Architectural University. And she's working on processing and utilization of bamboo and wood properties and application of biomass material. The title of the presentation is Effects of Hydrothermal Treatment on the Bending Properties of Moso Bamboo. The time is 10 minutes for your presentation. Please share your screen. Are you there, CGA? CGA, can you hear me?
我在的。
Okay, please share your screen.
稍等一下，我来共享一下我的屏幕。
Please bear with me for 1 minute after I share my screen with you.
可以看到我的屏幕吗？
Can you all see my shared screen?
Okay.
Yeah, we can see your screen. Please go ahead.
好的。各位专家学者，大家好啊！非常开心。
Experts, scholars, greetings to you all. I'm very delighted to have this opportunity to share with you my current research results and application of the bamboo materials. This is the background. Comparing to the timber industry, the bamboo industry is more scattered based on small workshops and low added value. Cannot compare with timber industry's concentration and industrialization. Low utilization ratio is partially due to the structure of the bamboo per se, because unlike timber, it cannot be cut into large DBH timbers. It can only be combined together as an engineering material. So based on different diameter, it can be sliced into different parts. Only small proportion can be used, and a lot of width. The utilization ratio is less than 60%, and the width of bamboo slices is less than 30 millimeter. So we can only use bamboo materials to produce flooring and vehicle floors, very low added value. So the origin of my project is based on the National Key R&D program during the 14th five-year plan period time. So our very purpose is try to improve the bamboo utilization ratio as well as improve the added value. We try to first develop the bamboo into bamboo slices and make them into the laminated plywood. But although the technology is not very new, but we seldom see the corrugated bamboo mat plywood. During the processing process, we understand due to the poor toughness of bamboo material, it severely limits the form of bamboo products. So we use some solution treatments, and we also use water bath treatment method. Based on the different temperature, you can see the concentration level, the differences with regard to elastic modulus and bending strength. It's negatively correlated to the temperature and the concentration. So with a longer period of higher temperature treatment, bamboo can become more flexible. But there were no matured treatment solution being seen. That's partially due to the mechanical nature of the bamboo has no linear relationship versus flexibility of the bamboo. Only at the concentration of 0.1 of the treatment solution, the specimens have small modulus of elasticity. This slide shows the radius of curvature. The darker the color is, you can see the higher percentage of the bamboo materials are. And the conclusion is when the concentration is 0.1 percentage, the toughening effect of bamboo is the most obvious. It explains why the toughness and the concentration level have no linear relationship. This is using FTIR testing method. You can see after this FTIR, there is a significant change in cellulose, hemicellulose, and the lignin in bamboo powder. Without treatment, you can see there is a small absorption peak here. In the interest of time, I would skip the detailed elaboration of this graph. Next, I want to talk about microscopic analysis. Due to different concentration percentage, you can see the bamboo fiber morphology is different. You can see the part of cavities when the concentration level is 0.1 percentage, and there is a severe collapse when the concentration level is 1 percentage. This again, you can see the vascular changes before and after treatment. This slide shows you the application of toughened bamboo. It can be used for the improved bamboo crafts. On the right-hand side is a light lamp. Previously, we used rattan to produce the lamps. But in recent years, due to the export control and ban from Indonesia and Malaysia, rattan's price surged in the international market. So we use the bamboo materials to replace rattan to cut the cost by about 70%. But as a downside, using bamboo to replace rattan. During the weaving process, it's very easy to break. Comparing to rattan, the flexibility of the bamboo is not as good. You can see a lot of breaking points, breakages. Previously, the company used manual or skillful workers to repair by using glues, adhesives, but it's very low productivity and high labor costs. However, after our toughened treatment, you can see before and after toughened treatment. On the left is before treatment, and on the right-hand side is the after treatment. You can see the radius of curvature is significantly reduced. And to some point, it can break, just like steel materials. That is before treatment, but after the treatment, you can see there's no breakage, no splitting of the bamboo. That shows the performance after treatment improved thanks to the absorption of the energy. The right-hand side two pictures showed the final result after the toughened treatment process. You can see this is a very large size product, but there's no breakages. These are the bamboo products and crafts already under mass production being exported to US and Nordic countries. After toughened treatment, you can see we can have a more diversified combination of products. Second application is to use this on the corrugated bamboo mat. It is a very good heat insulation result. It's already being widely used in the Qatar's World Football Cup. You see a lot of so-called container hotels. They use many steel boards for the construction of this container hotel. But the heat or insulation effect is not as good as bamboo boards, because a lot of complaints said with the air conditioning system, and then the temperature of the board can cool down very rapidly, but after a while it would raise again. This is the downside of steel boards. Originally, we can use steel plus foams to increase the insulation and keep the heat. We can use a bamboo, actually corrugated boards instead of foams. However, the bamboo boards very easy to break. You can see even before the lamination process, the board or the mechanical features already lost before adding pressures. You can see once the radius of curvature is the largest, then the toughness of the bamboo is the minimum. But our solution is toughened treatment. After this treatment, we can improve the utilization rate by 70%. Of course, this is only a lab test result. Secondly, we can have a wider selection on the wave distance, margins, and slopes. Next, the prospects of bamboo toughening technology. Currently, we know that a lot of inner decorations inside the automobile and aviation interior by using bamboo fibers. But due to the properties of fibers, sometimes it's not strong enough, not toughened enough, especially with a larger span. It's very easy to break. Especially for those unique shapes. It's difficult to apply traditional bamboo fibers, but with this toughened process, we can use bamboo fibers more widely. Previous speakers also talk about this fire treatment method.
And then the cellulose will crystallize, and the
It's okay. Thanks.
好的，好的。
Okay, I will finish. And with the thermal treatment to bend the tongue, it is not really easy to do. It's not very efficient. So our elasticity or the resilient ductility enhancement technology may be useful. Okay, I thank you very much for your listening. If you're interested in this technology, you can contact me through email. Okay, that's all. Thank you.
Thank you very much for those words, CJ New. I don't know where Christopher went, so I'll take over from him. We have our next speaker, who is Bei Jin from Xi'an University of Architecture and Technology, with a presentation called Study on the Axial Compressive Performance of Sprayed Composite Mortar, Original Bamboo Composite Columns, and Engineering Application. Jin Bei is a doctoral candidate in structural engineering of Xi'an University of Architecture and Technology. Is mainly engaged in the research of modern bamboo structure, and he has published 2 SCI papers, 2 EI papers, and more than 10 patents.
So, dear colleagues and everyone, can you hear me?
Thank you.
Okay, I will go through my presentation now. I'm from the Xi'an University of Architecture and Technology. I'm a PhD student. I'm talking about the study on axial compressive performance of sprayed composite mortar original bamboo composite columns and engineering application. So I will talk about background first. First, the construction sector has a low raw material and resource use efficiency with a serious pollution and energy consumption. So we really want to choose the best feedstock or best material for the construction. Currently, we try to be lightweight, environment-friendly, and sustainable. China has a huge production output of bamboo. Naturally, people are looking into bamboo as a possible candidate. Advantages include short growth cycle, green, eco-friendly, high strength to weight ratio, good deformability, and disadvantages include irregular geometry, initial natural defects, rot and moth-eaten durability issue. So when we combine the two sides, we try to use a composite design. In our team, we propose a new type of bamboo structure, sprayed composite mortar and round bamboo. And we published some papers in Chinese and foreign journals. We spray a kind of composite mortar composed of mortar combination, polystyrene particles, and mineral adhesives on the surface of bamboo skeleton. And after a period of curing, it integrates sound insulation, heat preservation, and fire retardation, and other structural functions. Okay, I will talk about the second part, the axial compressive performance of sprayed composite mortar round bamboo composite columns. It can improve the global stability capacity, fully utilize the materials. It is simple to fabricate and easily assembled. It is green in the whole process of construction and use. It's coming from round bamboo, and after using this composite structure, it's even better in terms of probency. I've designed specimen longer and shorter columns. We have round, short columns, and also we have the coated mortar or sprayed mortar coated columns, and thirdly, alignment, a composite mortar and a cross-section of a square, and also a round cross-section with a protrusion, and also aligned cross-section, round cross-section column. And also we can have some mix and match, just some dimension specifications of different specimens and the cross-section and loading mode. We have a foot section or only load onto the bamboo part of it. We are actually looking to the loading methodology of reinforced concrete within steel iron tube, and also some failure modes. The first short round column, and we can see the wall is fractured. B, C, D, E are composite. We have protruding, aligned, and square or roundish cross-section. We have the mortar failure or inward fracture of the column. And also for the slender column, at the two sides, we have local failure, but not along the whole length. And also analyzed some data. First, diameter of the bamboo. For a round bamboo short column, when the diameter increases, ductility will drop. But for the composite column, it's axial compressive strength, and the maximum strength will go up as the diameter increases. Secondly, with the sprayed composite mortar compared with short column, square vis-a-vis the round cross-section, you can see that the axial stiffness is not significantly improved, and the ultimate load decreases slightly. The ductility is greatly improved. And sprayed composite mortar, you can see this is a circular cross-section. The axial stiffness, ductility, and ultimate load are greatly improved in the circular cross-section. And this is the for the circular cross-section plus only bamboo pressed. You can see the axial stiffness and the ductility are improved, while the ultimate load is not. Here. This is the sprayed composite mortar slender column. After spraying the mortar, it will improve the stability, the axial stiffness, and ultimate load and improved, but the ductility is not, because it is shifting from stability failure to stiffness failure. Both ends, they have a brittle failure. So the ductility is not improved. Cross-section form for short column, full section loading mode. The mechanical performance of composite short column with a square cross-section are better than those with circular cross-section. With only bamboo compressed, the mechanical performance of composite short columns with both cross-sections are basically equivalent. Loading mode for short column square cross-section. The mechanical performance of composite short columns with a full section loading are higher than those with the only bamboo pressed, because the mortar and the bamboo will withstand the load, but with circular cross-section, the axial stiffness and ultimate load on the full section loading are higher. And when only the bamboo part is pressed, it has a higher ductility. And Standless ratio, basically the length to diameter ratio. And for the round bamboo slender column, the greater the slenderness ratio, the smaller the axial stiffness and ultimate load and the ductility. And also we are using the finite element model to have extended analysis to look into the height of the column as a factor. With the height of the column increasing, the axial compressive stiffness and ultimate load of the round bamboo slender column and the composite standard column decrease, but the mid-height lateral displacement increases. The ductility of the round bamboo column increases, and composite column is right the opposite. And also the thickness of the sprayed composite mortar layer. For the slender column, the axial compressive stiffness and ultimate load of composite slender column increase with the increase of the thickness of a sprayed composite mortar, but the ductility is basically unchanged. This one is initial bending of the round bamboo for the slender column. With the initial bending of the round bamboo increasing, the ultimate load of the round bamboo slender column and the composite slender column decrease. The round bamboo slender column, the axial compressive stiffness decreases, but ductility will increase. For the composite slender column, the axial compressive stiffness and the ductility are basically unchanged. The calculation formulae for the short column, we're using the elastic ultimate bearing capacity, just as if we are calculating the capacity of the reinforced concrete with the iron tube. And we are showing some fitting curves. And for slender column, our assumption is that it is thin walled axial compression member with a variable section and thickness, and initial bending hinged at both ends. So this is based on established balance equation, a mechanical equation formula. And then we can extrapolate the buckling capacity of slender columns on the axial compression. This is the validation result. The error is within the 10% range, indicating the effectiveness of the calculation method.
Could you finalize in 1 or 2 minutes, please? Thank you.
Okay, no problem. Just engineering application. In 2017, we have designed a single-story bamboo skeleton building. First, a bamboo skeleton installation applying waterproof materials and filled EPS board spray composite mortar, and then install the roof panels, roof waterproofing construction, And the whole building, in the end, is a real-life project and a simple conclusion. The first part is the failure mode of short column is the overall destruction of the bamboo. The failure mode of slender column is the overall buckling. Different factors have different effects on the axial compression performance. But all the details were presented before. Calculation formula of compressive bearing capacity of short columns is derived from the superposition principle. And the calculation of both formulae are valid according to the test. Thank you very much. You can contact me later for more questions. Thank you. Back to you.
Okay. Thank you very much for that presentation, Bei, and that was a very interesting presentation once again. I need to apologize to Rui-Ma, who I skipped in my introductions. I will pass over to Cristoforo to introduce Rui-Ma. Rui-Ma will not be delivering a presentation herself. She has a recorded presentation because she's not feeling particularly well. Over to you, Cristoforo.
Yeah, thank you, David. So the next speaker, as we said, is Rui-Ma. The presentation is recorded. A brief introduction about Rui-Ma, a PhD candidate from School of Engineering in Tianjin University, majoring in structural engineering. She's engaged in the study of steel and bamboo structure. At the present, she's doing the research on the fabricated bamboo structures with low cost, which is sponsored by the National Key Research and Development Project of China. The title of the presentation of Rui-Ma is Structural Grading of Moso Bamboo Column based on its maximum external diameter. I don't know who is starting the recorder, please. But Rui-Ma is here, right? No, she's starting the recording. Okay, please start the record.
Yeah, thank you, moderator. I'm really sorry to have to give my presentation in this form.
Okay, please.
Ladies and gentlemen, I'm delighted to have the chance to address you on this special occasion. The topic of my presentation is structural grading of moso bamboo column based on its minimum external diameter. The part of my talk are as follows. Well, let's move on the first part of this topic. In the production and construction process of traditional buildings using industrial materials such as steel, concrete, and brick, large amounts of greenhouse gases like carbon dioxide are released into the atmosphere, causing global warming problems. Biomass materials with the ability to store carbon are widely considered as substitutions of these conventional building materials, like wood and bamboo. There has been a long history of natural bamboo as an construction materials around the world, especially in the tropics and subtropics. Nowadays, there is still an ocean of bamboo structures constructed by bamboo columns in China. However, they are constructed on the basis of experience in general rather than using modern debentures, restricting the use of bamboo in construction. On account of their material, the geometric, physical, and mechanical properties of bamboo vary from one to another. To achieve the goal of standardized design, the foremost thing is to sort every piece of bamboo into specific grades. Attempts has been made to establish great methods of bamboo columns, but there are still some deficiencies remain to be improved. Most of existing studies focus on the classification process of natural bamboo to control the qualities of engineered bamboo products, which is not suitable for the use of bamboo columns in construction. So I also provide the principles and the procedures of grading bamboo columns when constructing bamboo structures. The specific grades of any bamboo species have not been defined. Meanwhile, bamboo clumps are supposed to be treated before utilizing in construction. Geometric, physical, and mechanical properties may be affected by different treatment strategies. The influence has not been considered before. Consequently, the study attempts to establish specific standards and give the characteristic values of mossel bamboo clumps with different treatments. Let's move to the methodology part of this study. As we all know, visual reading is non-destructive and easy way to sort bamboo clumps according to their geometric properties in practice. It's quite important and convenient to grade the bamboo clump with a certain geometric character. From the point of view of facilitating structural design, we hope also bamboo clumps could be designed like steel tubes. Thus, the diameter and thickness are two key parameters to represent them. However, the external diameter and thickness changes along the length of mossel bamboo clumps. Best safety results could be obtained designing according to the minimum external diameter. Therefore, mossel bamboo clumps could be regarded as ground types to facilitate the analysis and design mossel bamboo structures, satisfying all hypotheses. According to the market research results, we found out that the minimum external diameter of mossel bamboo clumps utilized in construction are mainly distributed from 60 millimeter and 130 millimeter. Thus, five grades of mossel bamboo clumps are presented as shown in this table. 653 mossel bamboo clumps with length of 2 to 3 meters are randomly selected as study samples, of which 210 were untreated, 283 were with chemical preservatives treatment, and 160 were in heat treatment, namely carbonization. All of the bamboo clumps were put in the same environment for 1 week to avoid the influence of the environment. Depth and perimeter were measured by the tip, while the external diameter and thickness were measured by the vernier caliper, and every clump were weighted by electric scales. External diameter of each end were determined by 2 ways, one of which is the average value of 2 perpendicular measurements made across offset points on the outer surface. Another is calculated by perimeter. The relation between the 2 methods is shown in the figure. It can be seen that the difference between them are generally within 5%. Meanwhile, measuring the meter is more convenient than measuring maximum and minimum diameters in practice. Therefore, the meter is recommended to determine the diameter of mossel bamboo clump in this study. As average, what thickness of smaller and larger end, external taper, internal taper, and linear mass are calculated based on the following formulas. Reduce the impact of sample size, bootstrap method is adopted for statistical analysis of dimensioned parameters of different grades bamboo. Let's see the results. As can be seen in this figure, the minimum external diameter of UT and CT are mainly distributed between 16 millimeter and 135 millimeter, while the value of HT is mainly distributed between 16 millimeter to 120 millimeter. Thus, it is strongly recommended that UT, CT, and HT could be divided into 5, 5, and 4 groups respectively. The distribution was thickness of smaller, and after 5,000 times, sampling is obtained. Representative results are shown here. The fitting results show that the distribution of both thickness is normal distribution. The fifth fractal is regarded as characteristic value and can be calculated according to this formula. The results are listed in this table. Comparing with characteristic wall thickness value of each grade, it can be seen that the wall thickness approximately linear increases with the grade growing, which means that after the external diameter, the thicker the wall. Wall thickness significantly decreases after treatment process in the same grade. The wall thickness of UT is larger than that of CT and HT. The influence of treatment is weakened gradually with the weight increasing. Results prove that the study of structure grading is essential for muscle bamboo can products with any new treatment technology. Conducting the same method to obtain the distribution of external and internal taper. According to the fitting results, the characteristic value can be calculated and listed in the table. Comparison of characteristic external and internal taper value between different grades is shown in the figures. It could be inferred that treatment process may increase the rational stability of muscle bamboo comes. Internal taper value has no obvious variety revelation, but fluctuates at a level of 0.38%. Thus, the characteristic internal taper value of every grade can be considered as 0.38% for convenience. For the distribution of linear mass, the value of UT is here by CT and HT, illustrating that the weight of muscle bamboo comes reduced after treatment due to the reduction of moisture content. The increase of grades linear mass increases approximately linearly. The increase rates of CT and HT are slower than that of UT, providing that the effect of treatment process is greater for the curves with larger external diameter. Let's move on the conclusion part. External diameter of muscle bamboo curve could be determined by the parameter in practice based on its external diameter. Muscle bamboo could be divided into 4 or 5 grades. Treatment process has great influence on the geometry and the physical properties. Wall thickness and linear mass reduce significantly after treatment process. The study of structural grading is essential for the products with any new treatment technology. And the most important of all, characteristic value of graded muscle bamboo curves is obtained in this study. However, this paper is a preliminary explosion of bamboo grading. Much more data is needed to validate and improve the results of the study in practice. Meanwhile, the study on the mechanical properties of each wood has been carried on recently. At last, I'd like to thank the sponsorship of the National Key Research and Development Project and Tianjin postgraduates scientific research innovation project for this study. I thanks to Professor Zhu Haishen, Associate Research Fellow Yan Shengzhu, and Lina Zhao for their help on this study. That's the end of my presentation. Thank you for your attention.
Well, thank you very much, Rima. That was a very interesting presentation. I'm going to certainly reach out to you to discuss some of those things you talked about grading. I found them very interesting. Thank you. Our final presentation is to be delivered by Daniel Hindman from Virginia Tech. It's called Evaluation of Tray Guide, Bambusa blumiana, Bending Strength Perpendicular to the Fibers Along Column Height. I don't have anything about. Oh, Daniel Hindman, PE, PhD, a lead green associate, is an associate professor in the Department of Sustainable Biomaterials at Virginia Tech and a principal faculty member in the Myers-Lawson School of Construction. Dr. Hindman teaches classes in wood mechanics, green building systems, design of wood structures, and timber engineering. Research and extension topics have included green building, design of wood structures, and construction safety. Dr. Hindman currently serves as the director of IC SAFE, the Center for Innovation in Construction Safety, Health, and Well-being. Recent research projects have included the use of US-based wood species for cross-laminated timber production, defining the loads placed upon trusses by workers falling, and the reuse and recycling of wood sheathing on green construction sites. Over you to Dr. Hindman. Thank you.
Thank you. Hello, everyone. Good to be with you. I want to acknowledge my co-authors who are, I have a long list of them. I will explain that a little bit later on. Myself and Jonas Hopman from Industrial Design at Virginia Tech have been the lead faculty members on this. This is a project that evolved from some of our other work that we've been doing. Just to state some introduction material, as we think about bending of panels or beams, we usually think about four things: the bending strength, the shear strength, deflection, and finally the bearing strength. And the bearing strength is the subject of what we'll do today. Our current research has been focused on studying lightly modified bamboo panels. So here is a diagram showing a cross-section of those. So we are taking relatively solid combs of bamboo. These are from Tray Guy, which is Bambusa blumiana, and using them. So we are flattening the tops of the poles or cutting the poles in half to provide glue area, but we're trying to maintain the section modulus of the pole section itself. And on the right is a image of one of these panels in testing. And as we started testing these panels, we started talking about where we should be placing the pieces of bamboo. And Jonas has a strong interest in parametric design. And so where we are able to actually look at the scanned poles of bamboo that we have and then choose where we want to place them within the composite. And kind of the question that started this was the first one here: should we try to place the nodes of the bamboo layers at support points for the beams? And as we talked about that, said it does, and I think common knowledge is that the we'll call it the crushing strength for now, but we'll take that apart in a little bit, or the bearing strength is stronger at the nodes. Anecdotally, we felt that, but we wanted to understand what is the difference between the node and the internode, and also how does crushing strength vary over the pole height. And so getting back to my large list of co-authors, these are my students who have participated in the 2019 and 2021 SBio 5324 Timber Engineering class. This is really a special topics class in timber engineering, mostly focused upon wood, but I've managed to stretch the definition of wood into bamboo. You could think of bamboo as kind of a rayless form of wood composites in a hollow section. And we combined our laboratory and classroom experiences with this course, and looked at literature, developed a research plan, and then conducted the experiments, and then some preliminary analysis. And I found this very helpful. The level of bamboo research funding support in the United States is very low. So for me, this was a nice option to be able to incorporate this into a class where I had kind of a ready workforce for me. And so myself and Jonas Hopman supervised the students as they conducted this. Our research objectives were to measure the, again, I think I'll use crushing strength for the last time here, because the correct term is bending strength perpendicular to fiber. And that's what's listed in ISO 22157. We used 8 different bamboo poles that were tray guy poles. These were commercially purchased and sent from Vietnam. So unfortunately, one of the disadvantages of my research is that we do not have an exact position of where each pole is located within the overall comb of the bamboo pole. So each of the poles is 4 meters long, and essentially we sectioned each of those 4 meter long pieces into about 50 centimeter lengths that then we tested for the bending strength perpendicular to fiber. We tested both internode and node sections. I do realize that ISO 22157 is only states that only the internode should be tested, the area between nodes, but we wanted to understand the difference between the poles, along the length of the poles, and with the node and the internode. And finally, as many others have done, we wanted to try to correlate the mechanical strength properties to physical dimensions of the bamboo poles themselves. So as I mentioned, we had 8 poles commercially obtained. We do believe they're Bambusa bloomiana. However, this is one of the other problems with importing this material commercially. It may have been Bambusa stenostachya, 4 meter long. They had between 19 and 21 nodes in that 4 meter section. And we cut them into between 38, 56 millimeter long pieces. So overall, we had something like 650 specimens. And this is chapter 15, the bending perpendicular to fibers. And we calculated the bending strength and stiffness terms. And again, just to think about this, is this a compression test or a bending test? Well, if we're talking about wood or a solid composite material, we would be talking about a compressive test here, where we have a uniform load throughout the entire section and a uniform stress following that. However, as we think about a ring, and then we think about a ring being compressed, if we take a quarter of that section and look at the forces on that quarter, we'll have a force from the top of the ring vertically, but then the corresponding force is going to be at the center of the ring with a moment arm, the distance of the radius. So what happens as you compress these rings is that that moment becomes the critical force within the ring, and that's what causes failure. So you tend to see a splitting of the rings, either what's called the north-south, which is the top and bottom, or the east-west, which is the right and left. Now, an essential part of doing ISO 22157 is to track the diameter and the radius of the rings. And we decided, rather than trying to measure with calipers and have difficulty with that, we would use some computer scanning. So we used Rhinoceros 3D. So we scanned the ring sections on a flatbed scanner and then imported those pictures into Rhinoceros 3D. And using several of the tools in Rhinoceros, we are able to pick points along the inner and outer ring of each, the inner and outer circumference of each of the rings, and determine the radius and diameter from those. So we felt pretty confident in this. Of course, there is a smoothing algorithm in Rhinoceros 3D, so we were able to get more of an averaged radius value that we could then use. This is the testing of samples. On the left, we have an internode ring, and you can see how this has started to fail after compression. We used a set of strips of rubber on top and bottom of the sample just to apply pressure so that force was not applied at one point. And the picture on the right, you can see is a node, and you can see about a 15-degree fracture going from the upper right to the lower left in that piece. Now, I said we tested some 600 samples as we did this with 8 poles, and data analysis then became our main challenge. And so here are some of our results. So this is the strength in MPa along the pole. There are 4 different strengths given for tension and compression in the north-south and tension and compression in the east-west. The north-south would correspond to the top and bottom, and the east-west to the left and right. What you're seeing here is the complete pole. So the points that are much higher or much lower correspond to the nodes versus the internodes. So to study the rest of the data for all this variability, we decided to separate the node and internode values into separate groups, and this helped us gain a little more understanding of it. We did see a lot of variability within these data sets, and however, the strength terms do appear to be normally distributed, and the stiffness terms were a log normal distribution. Overall, the strength values at the nodes were approximately 2.9 times the strength at the internode. And we did not really see a generalized trend in bending strength perpendicular to fiber along the pole height. If I go back to that image, and if you look at the, for instance, the black circles, starting on the left-hand side of this graph would be the bottom of the pole, and the right side would be the top of the pole. There may be a generalized trend, but you can see there's actually kind of more variation between the nodes sometimes than along the length of the pole. Then finally, we we tried to do some correlations of the different strength and stiffness values with the dimensions of the individual rings. So we used the outer diameter, inner diameter, and thickness, and these were the correlations we found meaningful. For the internode, the stiffness was correlated with outer diameter and thickness. For the nodes, the stiffness was correlated with outer diameter, inner diameter, and thickness. And then the stress, the compressive stress in the north-south and the tension stress in the east-west were both correlated with the inner diameter and thickness. I've got one more and I'm done. So just our conclusions were that we found that the scanning methods were very helpful with determining the diameter and radius, and we found this to be an effective learning tool to show students how to conduct research and get some research done that has less funding opportunities. And thank you.
Oh, that was a fascinating presentation, Daniel. I really very much enjoyed it, and keen to share ideas on how we go about researching with students as a way to overcome difficulties with funding. And the question. So I think we now enter the session of questions, and I've been scanning the questions as they come along. I don't know about you, Christopher, but I haven't seen that many questions popping up. Just one a moment ago. There is one that came right at the beginning.
Maybe we can ask to rewrite the question in case we missed. I think it's easier, right? So there
absolutely.
So if you have any question, please type in the chat, right? So it's complex for us to go through all the discussion, right?
Yeah. Well, I've only picked up 3 questions coming up. I have loads, but I've only seen from the audience 3. I don't know if you've seen any other. I'm going to start one I noticed a long time ago for Kent, which said, how to determine the pre-stress force required and can be without pre-stressing. Any requirement on the fish mouth joint example, gap allowed to cater workmanship constraint in producing the fish mouth joint. And thank you for sharing. So Kent, are you on the call?
Yeah, I'm there. Just a second. I'm going to share my screen if that's all right, because it's easier to point at. Can you see the presentation slides?
Yes.
Okay.
Yep.
So it's a good question. The very short answer is trial and error. A fish mouth joint on its own can only resist compression aligned with what we have as the beam element. Obviously, it doesn't have a tension capacity and it doesn't have a flexural capacity. By introducing the INBAR, we introduce the potential for a tension strut, in which case, as we showed over here on the right, we can get a tension compression couple where we have tension in the INBAR and compression at either the top or the bottom of the comb. And so that can be designed by simple mechanics. I mean, anybody who's designed reinforced concrete would recognize, in fact, this type of approach. How we determine the pre-compression force was actually by trial and error. We wanted the largest pre-compression that we could get, which would maximize the moment capacity without crushing the column, in which case we did a number of trials to make sure that we were in the right ballpark. And you can see the force that we ended up with. That's an average force. It did vary a reasonable amount of about 8,500 kilonewtons, which was fairly significant. And we, of course, ensured that a node was nearby, which helps us out. We are presently actually running tests that look at what we can, what level of INBAR force we could run based on, for instance, the size of the fender washer and what have you. And this will be forthcoming. So I hope that answers the question.
Yeah, well, I'll follow on with a question if you keep that slide open, Kent.
Okay, sure.
And
again, I remind you, and you know this, that the focus of this study was not the connection itself, but rather the methodology.
Yeah, I had two questions actually. One is that when you got open there, now you've mentioned the compression parallel to the fibers there being of the order of 36.5 megapascals. I struggle to imagine what would have been the stresses perpendicular to the fibers, knowing that they're much weaker, and how the failure would be governed by something in the parallel fibers instead of the crushing of the column behind. Can you sort of run us through what failure modes you were observing there?
Sorry, perpendicular to the fiber. I mean, there really isn't.
Yeah.
Because
there is perpendicular stress in the vertical column.
In the vertical column.
Yeah. Those stresses would be transferred.
It's sort of transferred. I mean, obviously the shear is transferred by friction, and we actually did not have a problem with crushing into the column at that particular location. It really was a failure on the beam element. Now, keep in mind the beam element, although it's drawn here, the beam element was very slightly smaller than the column element.
Okay. And the other question, did you check if these connections could be predicted using the ISO component capacities method?
I think you would struggle with it, partially because the bolt portion of the connection, this has a very low capacity based on the equations that we have in there, which you and I both know are very conservative. And so we would have, I got to be careful how I say this. We would have underpredicted the average behavior if we're looking at nominal types of properties. We actually would have been pretty good on the, let me pull up that slide. We would be actually reasonably good on the characteristic.
Okay.
That's more by luck than good management.
Okay, well, I'll pick up this one another day with you.
We get a lot to pick up on this, I assure you.
Christopher, have you picked another question? Because I have another one that I noticed that someone had raised.
I think there is a question in the chat box here, repeated from Jim. He's asking to Chuo, Meng, Luisa, what's stopping the industry to use clean tech, renewable energy to grow bamboo plus agroforestry, manufacture bamboo products, CLT, biocomposite, as well as in construction? Context, in ultra cost efficient things like solar thermal induction, AIESS plus microfactories exist that can further stay with the infrastructure buildings after construction, other is wasted, and it doesn't not use lithium or gas or any toxic chemicals. Who is willing to reply? In any case, Jim, if you are connected, you can unmute yourself, right? So, and you can ask directly. I read your question. Luisa, do you want to give some comments?
I can try to answer to the Italian, looking at the Italian situation. I think in Italy, first of all, there are not a lot of bamboo so far. It's growing, the plantation, so the material will be, more material will be available in the next future. But I think the two are the main limits of bamboo in this moment. One is a cultural feeling that bamboo in Italy is something that is exotic. And so there is some cultural feeling to overcome. And second is that is the standards. And also this is something that is something that we are dealing with. So I think also this is something that could be overcome.
That's good. As Italian as well, you know, I'm very happy to hear that you are more and more involved in the Italian development of bamboo. I don't know if we have other comments. Yeah, Jim replied to you. Thanks, Luisa. I cannot find any other question at the moment. David, I don't know if someone in the chat is willing to add some.
I have seen one question as well.
You want to?
It's from Pradeep Kumar, And I think it's a question directed to Daniel. And it's that this is either compressive or compression strength, but not bending strength. Can I get an explanation from the author? Daniel, do you want to tackle that one? Or shall we pass it on to the authors of ISO 22157?
Well, I'll take a stab and then let them fill in. But I hope my little graphic there cleared that up. That really it's acting kind of as an arch. Those quarter sections, and again the nature of bamboo, where there's no raise or cross structures. That moment now becomes the critical source of failure, as the ring is kind of pried apart.
Yeah. So I hope Pradeep is satisfied with that answer. I would complement by saying that when ISO 22157 was written, the intention was to describe what was happening to the fibers in that failure mode. And it's a prying, as you've just said, that occurs, and not a perspective from the point of view of the column, which yes, it looks like a crushing of the column.
And that is what we observed as we tested it, that the kind of the section would hinge at the top and the bottom, and break apart, and it really kind of broke along that cardinal direction, that north, south, east, west, into 2 or 4 pieces, as it did.
So it's a view of the point of view of the material and not of the section. Right. I have some of my own questions for the speakers.
David, can I just add to that comment a little bit?
Yeah, absolutely.
And I texted Dan like a private message. One of the concerns that I have in using that particular method with very thick walled elements is we definitely have an arching behavior, and that does change the resultant force at the east-west location a little bit. I would be, we think about thick-walled and thin-walled pipe, for instance, and we tend to think about D over T of 10 being the differentiator there when we're talking about pressure pipe. I think we do need to kind of look at this test and think about whether there is a differentiation and a slight change in behavior, whether we have a relatively thin-walled element or a much thicker walled element, as was shown in the images. It's just a comment. I think there's a little bit more differentiation that probably has to go on.
Oh, and I would add, when you have a node there, you probably have something completely different as well.
I don't think if you have a node there, you know what's going on personally. I think that we wouldn't do that. Personally, I wouldn't do that.
I think it would be interesting to look at this analysis also, not just in terms of stresses, but also in terms of capacities, to see if there's easy trends there as well. Okay, I have a few scattered questions, and maybe a few Christopher have as well. I have one for Luisa Malari, and it was that you've pointed out that there could have been some degradation to the non-fiber elements, sort of a parenchyma between the fibers. Are you intending to do some test that assesses the degradation to this sort of material? And what test were you thinking of?
Yes, do you mean for the UV damage, right?
And the heat damage as well.
Oh, okay.
The heat effect.
Yes, no, I was thinking to share test, something that something that is on the that test intra fiber material.
Yeah. And shear would be your choice.
Yeah, could be from the material, from the mechanical point of view. From the microscopic point of view, we already have seen that in both the case, in the heat treatment and in the UV ray, there is a damage. also the fibers get sort of delaminate, not delaminated. It's something that you can see the different layer of the fibers, but in the longitudinal direction, it's fine. I mean, there is no cut in the fibers, but on the surface, you can see the fibers the different layers of the fiber, for example. So both from microscopical point of view, we can look at it, or from the macroscopic point of view, I think shear test will be fine.
Yeah. Okay. Excellent. Thank you very much. I have another question for Rima. But I don't know if Christopher, do you have any questions that you would like to ask the presenters?
Yeah. Go ahead with the questions, David, and yeah. We have to try to close the session because in theory we have to finish now, right? So we have some
in a couple of minutes. Yeah.
I'll just sure. Yeah. But please go ahead with your question. Yeah.
Rima, I have a question for you. Of course, you're working in a topic very close to my heart, which is grading. And you talked about linear mass and how linear mass changed with the treatments. But what I didn't see in those analyses is whether you considered moisture content. Was this linear mass normalized to a certain moisture content, or was moisture content considered when you were measuring linear mass?
Thank you for your question. I put the bamboo in the same environment to keep them to the same moisture content, but I haven't tested the moisture content one by one.
Okay, thank you. Okay, Christopher, now we are drawing to an end.
According to the program, we have the closing words. So, David, absolutely. You have 2 minutes, and we have Durai Jaraman for 3 minutes.
Yeah, excellent. So we draw to a close of the 20.
Say, David, please go ahead, and then we will ask Durai to give a closing remark at the end of this very interesting session.
Thank you, Christopher, for working today with me. So we now draw to the close of the 2022 International Conference, Bamboo, a Very Sustainable Construction Material, and the 3rd World Symposium of Sustainable Biocomposite Materials and Structures. Thank you all, the team who have supported these sessions, from INBAR, the interpreters, moderators, and presenters. Over these 8 sessions, we have listened to fascinating presentations about bamboo, timber, and biocomposites. The advances in these fields are heartening and show that there are many like-minded academics and professionals keen to potentiate and promote these materials as a more sustainable alternative. Please look out for the publications linked to this conference, the special issue for bamboo and bio-based construction material in the journal Engineering Structures, the special issue in the Journal for Sustainable Structures, and the conference proceedings by Springer or Taylor Francis. And I now pass you to Durai Yaramadan from the Global Program Director of INBAR. Thank you. Oh, someone's asked, Wei Jin has asked for a group photo as well. So shall we go with the group photo now, or after Durai has spoken?
Now we are ready. I think we can take it now and then leave. Write a closing speech. We can smile.
Good.
So who is taking the photo? This is my only question. David, we cannot see you. I think your camera is off. I don't know if this is intentionally or not.
I couldn't see David, but I can see his figure. Okay, let's take it. 1, 2, 3.
3. Okay, thank you.
Thank you, Jinwai. Thank you, Jinwai. I think we can have the, yeah, okay. So firstly, we would like to extend the warm greetings to all the participants from INBAR in Beijing. Today, I'd like to thank David and Christopher for their excellent moderation. Today is the conclusion of the long 8 seminars which we had as a part of 2002 International Conference, the Bamboo, a Sustainable Construction Material. And it is also the 3rd World Symposium on the Sustainable Biocomposite Material and Structure. This series of the seminar and webinar happened during the past 2 months, in November and December. This includes the technical session as part of the Bamboo and Rattan Congress, which we recently had, and also INBAR UNFCCC COP27 side event at the Egypt. INBAR would like to thank the 37 organizations who partnered with us as the co-organizers and the supporting organization. Due to the limitation of time, I would not be able to mention all the aims. I want to assure you that INBAR recognizes and greatly appreciates the support received from all the co-organizers and the supporting organization. Thanks to all the speakers and moderators, we had approximately 90 to 100 speakers from the 8 sessions. The webinar had the registration of like 1,500 people from more than 70 countries. And the webinars and the seminars had some participation of online and physical, more than 1,000 participations. And then the recorded video, some published, had the views more than 4,000 times. The news of the conference was reported in 13 media outlets, the print medias, institutions, and blogs. And it was read more than 20,000 times or some people. Importantly, INBAR UNFCCC Innovation Hub organized a side event at COP27 at Egypt, which attracted more than 2,500 post-session views, which is almost 10 times as in most of other COP27 side events. So it shows that the construction seminar, the bamboo as a construction material is widely accepted, and it is an upcoming material, and it has a very green future. In closing, I would like to thank Huai, who is our coordinator of the Global Bamboo Construction Program, for her efforts in successfully organizing this 8th session, and also to my colleague Jinwai and Yu Chen, who provided the coordination and technical support. In closing, I wish all the participants, all the speakers, many thanks and great success on all the future endeavors they do. I formally close this webinar session. Many thanks indeed. Have a good night and good afternoon.
Thank you.
Buenas tardes.
Thank you.
Thank you.
Thank you.
Sumacho. Okay.
所以感谢2位同传老师哈。
好了，
非常辛苦。好的，感谢 Thomas。
See you next year, 秦卫。